Let's dive into the detailed step-by-step explanations for question 1, the multiple choice section. Starting with 1.1, the answer is D, 0. Moving on to 1.2, the answer is B, is 0. For 1.3, the answer is C, a light stationary object. In 1.4, the ball has the most kinetic energy just before it hits the ground after bouncing. For 1.5, the answer is D, 4E. In 1.6, the answer is C, change in momentum of a body. Continuing to 1.7, the answer is C, 2mv. Discussing 1.8, the direction of the electric field at point S is towards the positive 2 nanocoulomb charge, and at point T is towards the negative 2 nanocoulomb charge. Finally, in 1.9, the answer is B, there is only gravitational force present. These answers are key concepts to understand for the grade 12 physics mid-year examination.
The movement of block A is affected by several forces, with one of them being the kinetic frictional force that acts against its direction of motion. The free body diagram of block A illustrates the presence of the applied force F, normal force N, gravitational force mg, and frictional force Fk. The magnitude of the horizontal component of the applied force is 8.60 N, while the normal force exerted on the block is 34.7 N. Given a kinetic friction coefficient of 0.25, the frictional force can be determined. With an increase in the angle of the applied force, the horizontal component of the force decreases, thereby influencing the motion of block A. A proper understanding of these various forces offers valuable insights into the dynamics of block A. In Newton's third law of motion, it is stated that for every action, there is an equal and opposite reaction. This law is evident in the free body diagram for mass ma moving upwards, with tension T pulling upwards and gravitational force mag pulling downwards. The value of gravitational acceleration g is approximately 9.8 meters per second squared. Moving on to Newton's law of universal gravitation, which explains how particles attract each other based on their masses and distance. The acceleration experienced by a spacecraft at a specific position is approximately 1.2 times 10 to the negative 6 meters per second squared. Free fall, on the other hand, is the motion of a body where gravity is the only force in action.
In the field of physics, impulse is defined as the product of force and the amount of time over which it acts. When considering the collision involving car Q, the resulting velocity after the impact is calculated to be approximately minus 5.29 meters per second, indicating that it was an inelastic collision. Car Q has a mass of approximately 2.27 kilograms. On the other hand, block X is subjected to the influence of conservative forces such as gravity. The free body diagram of block X illustrates the various forces at play, including the applied force pushing the block up the incline, the gravitational force pulling it downward, the normal force acting perpendicular to the incline, and the frictional force opposing the motion. After block X has traveled a distance of 3 meters up the incline, its speed is measured to be around 3.87 meters per second.
When a ball reaches its peak velocity, it is at the point where it is moving at its highest speed. This is the moment when the ball is exhibiting the maximum amount of kinetic energy, which is the energy possessed by an object in motion. The velocity of the ball not only indicates its speed but also the direction in which it is moving. At its peak velocity, the ball reaches the highest possible level of kinetic energy. This energy is crucial for the ball to continue its motion and to overcome any resistance it may encounter, such as air resistance, as it travels through the air. The kinetic energy of the ball allows it to maintain its momentum and propel forward despite any obstacles in its path. The orientation of the electric field is established by determining the path that a positively charged test object would take if positioned within the field. When this test object experiences a force in a specific direction, that particular direction is recognized as the orientation of the electric field at that particular location. The electric field lines consistently show the trajectory that a positively charged object would follow when placed in the field. Therefore, The orientation of the electric field can be determined by observing the direction in which a positively charged test object would either accelerate or experience a force. This method allows for a clear indication of the electric field's orientation based on the behavior of positively charged objects within the field.
Impulse can be described as the outcome of the force exerted on an object multiplied by the duration of time over which the force is applied. This key concept is essential in physics as it signifies a vector quantity denoting the alteration in an object's momentum. As a force interacts with an object for a specific period, it leads to a modification in the object's velocity. The impulse encountered by an object equates to the momentum change it encounters. Essentially, impulse serves as a metric for evaluating how a force influences an object's motion across a time frame, putting emphasis on the interconnection between force, duration, and momentum.
Conservative forces, such as gravity, are those forces that perform work regardless of the chosen path. These forces are solely reliant on the initial and final positions of the object, preserving mechanical energy in the process. When examining block X on an inclined plane, the free body diagram illustrates various forces at play: the applied force directed upwards along the incline, gravity pulling the object downwards, the normal force acting perpendicularly to the incline, and friction opposing the motion. By considering these forces, we can determine that the velocity of block X after traversing 3 meters up the incline is approximately 3.87 meters per second. This calculation is derived from analyzing the energy acquisition by the block as it ascends the incline, considering the work performed throughout the process. In the investigation, the distance between charges, r, has been carefully controlled as the independent variable to ensure that the test results are solely influenced by changes in the dependent variable. According to Coulomb's law, the electrostatic force, F, between charges is directly proportional to the square of the product of charges, Q. The gradient of the graph, approximately 2.5 times 10 to the power of 9 n c²2, represents the rate of change of force concerning the square of the charge product. By analyzing this relationship, researchers can gain valuable insights into the nature of electrostatic forces and how they function in different scenarios, enhancing our overall understanding of this fundamental aspect of physics. Electromagnetic induction is the process of creating an electromotive force, EMF, by altering the magnetic environment of a conductor. When a conductor is subjected to a changing magnetic field, an EMF is produced, which in turn can induce a current in the conductor. Faraday's law of induction states that the induced EMF in a circuit is directly proportional to the rate of change of the magnetic flux through the circuit. Lenz's law dictates that the direction of the induced EMF and current will always oppose the change in magnetic flux that caused them. This concept is rooted in the conservation of energy. The photoelectric effect is a fascinating phenomenon in which electrons are emitted from a material when it is illuminated by light of a specific frequency. This effect demonstrates the remarkable ability of light to transfer energy to electrons, providing evidence for the particle-like behavior of light. Albert Einstein's groundbreaking photoelectric equation, E_k equals hf, phi, further elucidates this concept by establishing a relationship between the kinetic energy of the emitted electrons, the frequency of the incident light, and the work function of the material. The threshold frequency, a crucial aspect of this phenomenon, denotes the minimum frequency of light required to initiate the emission of electrons from the material. This underscores the precise energy threshold necessary to liberate electrons from the material's surface. Einstein's equation helps explain how the photoelectric effect works by showing the connection between electron energy, light frequency, and material properties. The threshold frequency indicates the specific energy level needed to release electrons from the material, highlighting the importance of precise energy requirements in this phenomenon. The concept of wave-particle duality is a fundamental principle in quantum mechanics, suggesting that particles, such as electrons, can exhibit both wave-like and particle-like properties depending on the experimental setup. According to de Broglie's hypothesis, particles possess an associated wavelength, which is determined by dividing Planck's constant by the particle's momentum. This wavelength is responsible for the wave-like characteristics observed in particles. By utilizing Planck's constant, the mass of the particle, and its velocity, one can derive the de Broglie wavelength using the formula lambda equals h m times v. This concept serves as a crucial link between the wave and particle aspects of quantum entities, aiding in our understanding of their behavior.
I heard you want to school from home, then roll at Dexter. Best in phone line, only 4 grades, 10 to 12, enroll right. Now register today.